So we're going to continue this, hopefully get done with this last part of the this PDF file. So basically what we said so far is, oops, sorry. What we said so far is that the number of chains that pass through the interface is this quantity is a function of time and actually temperature. But it takes, after a certain amount of time, which I call tau zero, this value gets the equilibrium, its equilibrium value. And because n is proportional to square root of x, we said it's proportional to, it's proportional to average delta x is proportional to a square root of delta x squared. And the reason I introduced this quantity here, delta x squared, is because this quantity appears in the diffusion equation. So if instead of that, by using the diffusion equation, I put this quantity here, then I can, and instead of nt, I assume that it's proportional to the energy per unit area that it takes to open the crack. Then I get this equation becomes the same as this equation. Now here I have used different temperatures, and times are not the same either. So for instance, if at temperature of T2 above Tg, it takes tau zero to get to this equilibrium state and recover the properties of the virgin material, at a temperature that's lower, T1, and a time that is less than tau zero, the energy release rate will be this much, will be proportional to this quantity here, this product. Now, from fracture mechanics, we said the ratio of GC is equal to the ratio of strength squared. I hope you remember that. So that allows me to equate this quantity with this quantity. It allows me to equate this quantity with this. And that's a very, very important relationship because, for instance, one of the things it tells us this equality is, if I go to the next page, is that if temperature is kept the same, the healing strength scales with T to the power of 1/4, because this is a square, this is a square root. So strength versus T to the power of 1/4 scales linearly as a function of T to the power of 1/4. But then at some point it reaches the equilibrium state. That is the strength of the virgin material. So in other words, this quantity here is sigma F0. That's the property of the virgin material. But also the equation we derived in the previous page allows us to make some even more sophisticated guesses, because I can also talk about temperature. I can discuss temperature as well. So I can say strength to the power of 2 is proportional to this quantity. And I know that the diffusion constant scales with temperature like this. That's the activation energy. This is K or R, depending on EA is per molecule or per mole. And so the combination of these two this equation and this equation allows me to tell you, if you increase temperature, if you do this self-healing, intrinsic self-healing, at a certain temperature above TG, how does it scale with time? And if you know that relationship for a certain temperature and time, you can do it for any other temperature above TG and any other duration of time. Oh, but, however, keep in mind that in all of these calculations, we are talking about temperatures above glass transition temperature. And the reason for that is that chain mobility below TG is very limited. We have motions of segments of polymer chains below TG, but we don't have that transfer of reptation, like the motion of the snake. We don't have that at temperatures below TG. So all of this only applies to temperatures above TG. So with that in mind, if I go back to the slides we discussed, you see, so these are the results that we got from the notes. I'm not going to repeat them to you. But what is very interesting is that you see this exactly this. This is, for instance, this is K1. Stress intensity factor as a function of time. It calls it penetration time. That's because it's the time that it takes for polymer chains to go from one to the other. And so these are different temperatures of healing. And you clearly see, as I go to higher temperatures, the healing is faster, is clearly faster. And all of them, the time scale is a log scale, follows a line because the relationship between K and T, or sigma, K or sigma is proportional to T to the power of 1/4. So if you put in a semi-log scale, this is going to be a linear relationship. Now, one thing in healing of thermoplastics becomes very important is the concept of crazing versus crack, craze versus crack. So if this is if I'm advancing the crack tip, at this region, inside this region, you have polymer chains that are still have one leg in one side, the other leg in the other side, and the crack tip has not opened enough so that these polymer chains can take side. They can still span the whole gap between the two sides of the crack. But if you look at the regions here, these are truly traction-free. This region is not traction-free. This region is traction-free. So basically, these are regions that are not traction. These are regions that are traction-free, and these are regions that are not traction-free. So what we call this region that has the polymer chains that are spanning the gap is, we call it craze. The rest of it is actually the crack. So the crack tip is where all the material that is on one side of the crack tip is traction-free. All the surface that is on one side of the crack tip is traction-free. Basically, all this surface and all this surface is exactly traction-free. So in that sense, this point is the crack tip. This point is the crack tip, whereas this point is the craze tip. Now, and you can, and so when the healing starts, you actually start developing these crazes first and then it becomes like a fully joined interface. And so I just want to show you in this sample, this is we basically, not we, in a research group, they looked at this portion of the material and this portion of the material, the crack face. They looked at the crack face after the crack has fully opened. This is the cases when they polished it, and this is the case when they left it unpolished. So imagine all of these things you see, these roughnesses you see, are parts of the polymer that was parts of the craze that eventually, when the crack opened up, they completely snapped. The polymer change snapped. So this is when the crack opened up, and now I'm looking at this surface. This is where it used to be the crazes. I'm going to stop this video, and we will continue on the next video. Thank you.